The physics behind a rocket launch is terrifying. It is not a smooth ride into the sky. It is a violent chain of pressure, fire, vibration, acceleration, and structural stress, where thousands of parts must work in perfect timing. Because if one valve opens late, if one fuel line leaks, if combustion becomes unstable, or if the structure shakes beyond its limit, the mission may not fail in space. It may fail catastrophically before it even leaves the launch pad. From a distance, a rocket launch looks beautiful, a bright pillar of fire rising gracefully into the sky. But up close, it is one of the most violent events in engineering. Before liftoff, the rocket is already carrying an enormous amount of stored energy. Most of its mass is not engines, computers, or payload. It is propellant. Depending on the rocket, that propellant may be liquid oxygen and liquid hydrogen, liquid oxygen and methane, liquid oxygen and refined kerosene, or solid propellant packed inside massive boosters. These chemicals are chosen because they can release huge amounts of energy very quickly. But that also means a rocket on the launch pad is not just a machine. It is a skyscraper-sized bomb that engineers must convince to burn in exactly the right direction. In a liquid-fueled rocket, fuel and oxidizer are pumped into the engines at extreme pressure. This is necessary because rockets cannot rely on oxygen from the air once they climb high enough, so they must carry their own oxidizer. Inside the combustion chamber, the propellants meet and ignite. And this is where the danger begins. The timing must be perfect. The mixture must be correct. The pressure must stay within limits. If too much fuel enters, combustion can become inefficient or unstable. If too much oxidizer enters, temperatures can rise dangerously. If propellants collect before ignition, the engine can suffer a hard start, a violent pressure spike that can destroy the engine. And if that happens on the launch pad, the entire rocket can explode before it even moves. A rocket does not simply turn on. It has to survive being born. Inside the combustion chamber, temperatures can reach thousands of degrees Celsius, hot enough to melt many metals. The pressure is enormous. Expanding exhaust gases are forced through the nozzle at incredible speed, creating thrust. The byproducts depend on the propellant. Hydrogen and oxygen mainly produce water vapor. Methane produces water vapor and carbon dioxide. Kerosene produces water vapor, carbon dioxide, soot, and other combustion products. Solid boosters can release aluminum oxide particles, hydrogen chloride, water vapor, and other gases. But the exhaust is only part of the story. The real terror is what that energy does to the rocket itself. The engines do not simply push the vehicle upward, they shake it. They send vibrations through the structure like a giant metal earthquake. These vibrations come from the engines, turbopumps, exhaust plume, airflow, and even the movement of fuel inside the tanks. That fuel movement matters. Thousands of liters of liquid propellant can slosh as the rocket accelerates and turns. If uncontrolled, that shifting mass can disturb guidance and stability. Engineers use internal baffles to reduce sloshing because even the fuel inside the rocket can fight against the rocket. Then there are turbopumps, extreme machines that force massive amounts of fuel and oxidizer into the engines every second. They spin at incredible speeds while handling cryogenic liquids, extreme pressure, and vibration. If a turbopump fails, the engine can starve, overspeed, rupture, or explode. Another danger is combustion instability. Combustion must stay smooth. But pressure waves can form inside the chamber. If those waves grow, the engine can pulse violently, almost like it is beating itself apart from the inside. In extreme cases, instability can destroy an engine faster than humans can react. While the engines fight combustion, the tanks fight pressure and temperature. Liquid oxygen is extremely cold and can make materials brittle. Liquid hydrogen is even colder, very light, and difficult to contain. Methane also needs cryogenic storage. Kerosene is easier to store, but produces more soot. Every propellant choice is a trade-off between performance, complexity, density, and cleanliness. At liftoff, the rocket is being crushed and stretched at the same time. Gravity pulls it down, thrust pushes it up, tanks press outward, engines hammer the base, the atmosphere pushes against the body. As it climbs, the danger changes. Near the ground, the air is thick. Drag and wind load increase as the rocket accelerates. One of the most dangerous moments is max Q, maximum dynamic pressure, when the rocket experiences its highest aerodynamic stress. The rocket is moving fast, but the atmosphere is still dense enough to fight back. That is why many rockets throttle down near max Q. Not because they are weak, but because even the strongest rocket has limits. After max Q, the air thins, fuel burns away, and the rocket becomes lighter. The same engines now push less mass, so acceleration increases. Astronauts feel several times their body weight pressing them into their seats, while satellites endure vibration, acoustic energy, acceleration, and shock. Even stage separation is dangerous. If stages do not detach cleanly, the upper stage can collide with the lower stage, lose control, or fail to reach orbit. And the rocket is steering the entire time. It does not simply go straight up. It slowly leans sideways in a gravity turn, building the orbital speed needed to keep falling around Earth instead of falling back to Earth. So a rocket launch is not just about going upward. It is about surviving ignition, combustion, fuel pressure, vibration, max Q, stage separation, and acceleration, all inside a machine that is actively trying to destroy itself. And when everything works perfectly, we call it a beautiful launch. But beneath that beauty is one of the most violent engineering events humans have ever created. A rocket does not gently leave Earth. It fights Earth. And for a few terrifying minutes, it wins. So here's the question. What do you think is the most dangerous part of launch? Ignition, fuel pressure, vibration, max Q, or stage separation? Drop your thoughts.